classification. So usually consider a two-class problem where there is a sample exists of two measures. So whenever you have the two-class problem, the sample is a combination of two values, one input and relevant output value, x, comma, y. So in the k nearest neighbor, what we are doing, we are considering the neighbor. Suppose like you have a query point q and we can assign the class of a nearest neighbor to it. So suppose you want to assign a class, so we'll assign only those class which is the class from the neighboring one. So like if k is equals to 1, k is equals to 1 means you are considering only a single value or a single neighbor. So this is a query point. The black star represents your query point and you are considering to identify this query point. What is the class label for this? You just considering its single neighbor, nearby neighbor. And if you are considering a single neighbor, then we called it k is equals to 1, or we can say one nearest neighbor rule in that case. So similarly, if you are considering k is equals to 3, like query star, black star is related with 3 different data points, which is nearby data points to this black star. And the value is 3. So you can take any value, and if you are considering all these values, nearby points to classifying this particular query, then it is called a k nearest neighbor, where the value of k is variable. You can take any of the values for deciding the class label for your query term. Okay, so suppose a value of k is equals to 3 here. So now let's see what is a k nearest neighbor. When we interpret the record as a points in the data space, we define the concepts of neighborhood. And what is the neighborhood? The records that are close to each other is called it's a neighborhood. Residing in the nearby is a neighborhood. So record of the same time will be close to each other in the data space. So obviously, whenever you are working with any points that could be represented into the data space, so those points which are closer to each other, they are called neighboring points. Like very good example is that the customer of the same point will show the same behavior. So usually recognizing the similar kind of customers will show a same kind of behavior, like the purchasing history. If a like of a customer is same with the like of other person, so usually they will buy a same type of things. So this kind of problem can be solved by k nearest neighbor. So basic principle for deciding the k nearest neighbor is do as your neighbor do. Okay, so do as your neighbor do means the class label which is categorized by a neighboring class will be similar to you also. Okay, so suppose if you are calculating the 10 nearest neighbors, so the value is 10. And finally, you will take the average of these 10 neighbors. Okay, average is like majority voting. If you're considering the 10 nearby points, so if the majority from the 10 near points are looking for a particular class, then you will also like the query that you are categorizing will also be the part of that part. What we mean by majority voting? Majority voting means suppose 10 is there and 8 are categorizing as the C1 class level. So obviously जो new data भी आएगा वो भी किससे belong करेगा? C1 class levels. And the value of k is variable. So it will define the number of neighbors. So what neighbors you are looking around you is basically the number of neighbors. If you are taking 5 nearest neighbor, the value of k is 5 and you're looking for 5 neighbors around you. It's like that. So there are so many issues in that because it's an expensive process. Expensive process is because you have to do lots of comparison in that. So that's why it is called an expensive process. Like if you want to find a nearest neighbor for a particular query queue, so there must be computation of n training examples. So like q point will be compared with all the 10 points and the distance will be calculated. For that purpose, we use the special data structures like KD tree. KD tree is k dimensional trees. Then we calculate the approximate distance that is LHS distance or Euclidean distance. So these are also used. LHS are basically your locally sensitive hashing functions. So it's a combinations of your Euclidean distance. So you can take LHS distance or simple Euclidean distance can be used. And then we'll work upon the remove of redundant data, and that is your condensing. So condensing will be used to condense the data from the to a localized one to become a local cluster, or the combinations of the points which are very close to each other, and where we remove the redundant data also. Then the storage requirement is also very high, because before the condensing, we need to store all the training data. For the pre-sorting of the storage requirement, you have to do the storage capacity. You need a storage capacity. So storage requirements is also very high. And the last one is high dimensional data. So it's a curse of dimensionality, because you are representing a tree with your KD trees, like it's a dimensional tree. One point linked with any other points related to each other. So it's highly dimensional data you are working with, and you need a partitioning techniques to degrade the linear search, because partitioning algorithm will divide your data into certain parts where you can get the local cluster, and you will find which are your close neighbors and which are your distance neighbor. So we are only consider those points whose equivalent distance is less in comparison to other. So what distance measure are used? Often the Euclidean distance is used. Then we have locally adaptive matrix, and there is non-numerical data for different dimensions had different scales. So it depends upon the data you are working with and how you are representing that. So if the data scales are different, then we first convert it, and then we'll calculate the distance between these two. Okay. So sometimes we'll do cross validation, and one KNN often performs well in practice, but usually KNN needs to overlapping classes. When you have overlapping classes, then it is used for KNN. So for those problems who are not solved with KNN or 1NN, then for that purpose, we need to do editing of the data. Okay, so here we have the asymptotic error. This is infinite sample size. It is less than the twice of Bayes classification error. We'll talk about Bayes classification error when we are discussing the Bayes classifier. Okay, so usually it has a less error in comparison to Bayes classifier, and it requires lots of training data. Expensive for high dimensions. Suppose D is greater than 20, so it's a D-dimensional space. 20-dimensional space is like that, and it's obviously very costly, or complexity is very high, because complexity is like O and D, where N is your number of training example and D is your dimensionality of each sample. So to reduce that, we perform the data editing or condensing of the data. So look at here, these are your decision regions. If you look at this data, so these are clearly, it can be shown there are two kind of classification. One is the points which are denoted with red circles, and the one point which are denoted with blue squares. So we can easily identify with eyes that these are the two class problem where the data is divided into two different classes. So to draw this diagram, we use the Voronoi diagram, which divide the space into number of cells. Okay, so each cells contain a sample, and every location in the cell is closer to that sample than to any other sample. Okay, so in the cell we have a data point, and that cell is closer to that point in comparison to the other points. And Voronoi diagram can be used to divide these data points into number of cells. So each query will be assigned to the classification of the sample within the cell, and the decision boundary separates the class regions based on the 1NN decisions rule. Okay, so we have the different kind of decision boundary. Here you can see a decision boundary with the dark dark black line which are separating these data points into two parts. Maybe it is not visible in that diagram, but this is the decision line, because you can see one portion is at the darker side and one portion is represented with a gray, and one portion is represented at white part, and between these two we have a decision boundary. So this is our decision boundary. Okay, so gray portion is those points which are classifying in a particular class, and white portion are those points which are classified as another class. So knowledge of this boundary is sufficient to classify any new point, because if you know the boundary of that, you can easily classify any new data. What is the other method? What we do? The condensing is other method. We have the condensed near neighbors also. So condensing is the process which aims to reduce the number of training samples, because as you have the lots of training sample, your representation space is that much dimensions. Okay, so to reduce the number of samples, why we are reducing it? Because to generate the data or to generate the algorithm on the basis of complete population is a difficult task. So what we are doing, we are taking a part from the population. Population is your complete data set. Okay, so we'll take a part of that training samples which represent your whole population. Okay, it's a kind of replica. If we apply any algorithm for that partitions of the training sets and if it give appropriate results, then it could be applied for complete population. Like it could be applied for a complete data sets. Okay, so suppose you have so many points, so we'll try to reduce the number of training samples by using condensing. Okay, so it will retain only those samples that is needed to define the decision boundaries. So only those samples are considered which can appropriately divide your decision boundary into two parts. So we have two kind of parameters, like the one is decision boundary consistent, another one is minimum consistent set. So here if you look at this diagram, you can easily find the difference between these three. And what is the difference? Let me tell. First is decision boundary consistent. Decision boundary is basically a subset of those nearest neighbor decision boundary that is identical to the boundary of entire training set. That I have already told you, if we reduce number of samples, but while reducing the number of sample, we have to take care that the boundary which we are choosing, that should be fit for the original data as well. Because you're reducing certain points, so it could be possible the boundary cannot be appropriately chosen. So we only remove those points which are not taking part in deciding the decision boundary. So look at this. First one is the original data. Like the original data, we have so many points. Then from the original data, you can see there is a decision boundary. It is shown here. We have to identify actually this decision boundary. Okay. So we perform a condensed data. So condensed data, we only take 3 points from the blue area. So blue, there are two different points. One is represented by the square sign and one is represented by the circle sign. But in the picture of the condensed data, we are only considering 3 points from the blue dots. So those are having the bigger circle, only these points are considered. And the bold stars, 4 different bold stars are considered in the second class. So what we are doing, we are only considering the 7 different values from the whole population. So in the original data, you have complete data set. All the points are represented here. But in the condensed data, you are working with only few points. Like from the class 1, they are taking the 3 points, and from class 2, they are taking the 4 points. Now we have generated a decision boundary, and this is called decision boundary consistent. Because by taking only these 7 points, we have generated this boundary, and this is very similar to the original data boundary. So this is the work of the condensed data, that you are selecting few numbers of the data points and the generated decision boundary is similar to the original ones. So apart from that, if you are not taking the condensed data, then we have the minimum consistent set. And minimum consistent set is like you can say a trade-off between original data or the condensed data. It is a smaller subset of the training data that can correctly classify all the original data. Okay, so this is called minimum consistent set. If you look at the boundary region, this is just a straight line, but it can divide the data into two parts. So from the one side of the line, we have the blue points, and from the other set of lines, we have the red points. So this is called minimum consistent set, which is like the smallest subset of the training data, and it can be easily classify your original data set. So just by putting a straight line, we can easily classify that. Now suppose this is a condensing nearest neighbor. As I told, in the condensing, what we need to do, we initially start with a single training example, and then we go on increasing the samples. Okay, so if it is not correctly classified, we removed it and we again repeat the step. We'll take a new data and we'll check again. Like in this manner, the CNN will work. Okay, so if you look at this data, here the first point is taken as this one. So, here this starting point is this. Here the starting point is another one. Okay. So like if we take this starting point, then the decision boundary is like this part. This is the straight line which is separating this, and this is the horizontal straight line if we are considering this particular point. So condensing is basically depends upon visualization of the data from which point you are starting. Then again, we'll continue with the same method. We'll consider other points and divide the data. Then we'll consider other points and divide the data up till dividing the data till we reach to certain classifying. If you look at this data, so there is a kind of misclassification because the blue dots are here inside the gray region. Okay, whereas in the right hand picture, there is no misclassification. So we'll again remove this and again repeat the same step. So in this manner, we can use basically condensing to combine the data and to generate a decision boundary that could be suitable for your original data as well. Okay. So condensing aims to retain the points along the decision boundary. So for that purpose, we are using the proximity graphs, and we have so many numbers of the proximity graphs like nearest neighbor graph, minimum spanning tree graph, relative neighborhood graph, Gabriel graph, and Delaunay triangle. I'm not properly able to pronounce this. It's a Delaunay graph. It's basically equivalent to your Voronoi diagram. Okay, so if you look at this, it's a subset of all these. So NNG is the less complex one. Then the minimum spanning tree is a complex one in comparison to NNG. And then RNG is much complex than the previous two, then GGG and DT. It depends upon your problem domain. So which graph is appropriate for donation purpose. Actually, if you are representing is nearest neighbor graph, it's easy graph. One neighbor is connecting with other neighbors. And then when MST is minimum spanning trees, then here we are taking the, actually we are drawing the circles by taking the radius, and then we draw the perpendiculars like this. So in this manner, these graphs are used. So let's see, the first way is Delaunay graph. If you look at this, what they are doing, they are just drawing a circle here and they are drawing the perpendiculars from it, and that perpendiculars are used to show the distance between these two, or whether they are identical or not. So it's a triangular function here, and it is very similar to Voronoi graph, because Voronoi graph, what they are doing, where they are converting the data into cells. And in similar here, we are making a triangular functions here in between the data points. Then we have the Gabriel graph. It is similar to the previous ones, in which in the Gabriel graphs, basically we have the reduced radius size in comparison to the previous one. And then we have the RNG functions. It's also similar. It's just a subset of the Gabriel functions in which we are not taking the exact circles. We are not taking the radius from one point to another point. Actually, what happened when you are drawing these graphs, we are taking the point as a center and we are drawing the circles. And then we are taking the relationship between these two. So all these graphs are very similar to each other. So let's see, suppose this is a data set. It's a, now we'll performing the editing. So it's the training set is noisy and overlapping classes. Here you can see this is not as such as similar to the previous diagrams. What is happening here? There are so many overlapping classes because blue squares and the circles are overlapping to each other. So for that purpose, we need editing. Okay, so to remove the noise and to produce a smooth decision boundaries. Okay, so that we can separate the data from each other. Here you can say the decision boundary cannot be a single linear lines or something like that, because what happened? You cannot separate the data from the linear lines or maybe choosing a simpler decision boundary. Here you have to aggregate the data into certain clusters form, and then you can apply, then you can generate the decision boundaries. Okay. So like this is the previous example where the two data are very can be easily separate from each other. So Wilson editing can be used to separate this. So first the Bernoulli diagram is used, which divides your data into your data points and divide the data points into the cells. And after the editing, we can have a decision boundaries. Like in the Wilson addition, the k equal to 7 is considered here and k equal to 7 is considered here also. And after that, we'll have a decision boundary. So all these functions are available in the MATLAB. You can just directly use these functions to draw the graphs, to draw the editing functions and all these. As well as in R, these functions is also available. I don't know about the Python, but maybe possible in the Python, these functions are automated available. And this is also multi-editing, where we'll talk about this. So first we'll draw the Voronoi diagrams which converted into cell, and from the multi-editing, what they are doing, they are making small clusters of these data points. Okay. And here you can see a different kind of decision boundaries with the available data. It's like multi-edit of 8 iteration, last 3 are same. Like after the 8 iteration, you come to this point. So these are the editing terms where you are not performing the condensing of the data to generate that decision boundary. Here you're performing the editing, multi-edit or Wilson added functions. Now it is the combinations of your editing and condensing where you are taking the smaller data points as well as you are performing the editing as well. So Gabriel editing is used to check the neighboring points from one point to another, as well as editing and condensing are also used here. So that's